For this example, I'm going to use the dataset included in the first of the two files that you have available online in Blackboard. So I'm going to be using now the file called lineup data version 1, and you will be using lineup data version 2 for one exercise that I'm going to propose you at the end of the online session. But I'm going to use this data set for testing a few assumptions that parametric tests will require. First of all, let's have a look at the data set. Let's remember what we have here. So we have one column with the participant codes. So 1, 2, 3, 4, 5, 12, and then 24. But then look at this 5. So some of the participants did not go through all the levels of the independent variable. In this case, independent variable was gaze direction or closed ties. So, for instance, participant 1 was looking at the left, but then he wasn't looking at the center, and no, there was no data also for participant 1 looking at the right. So basically, participant 1 was looking at the left and closed eyes. So basically we have different participants experiencing different levels of the independent variable. And of course all of them had measures 1 week after they watched the video and 6 months after they watched the video. So we have different levels of memory, to put it like that. Right, so we're going to do 3 things. The first one is to test if these data are normal distribute, so they follow the normal distribution. Let's go to the probably more straightforward one, and that would involve exploring the data. And we have a box for the list of dependent variables. So we have 2 columns, 1 week and 6 months, that we have to put in the dependent list. It's important to remember that they are not actually 2 dependent variables, but they are 2 levels of the dependent variable. And the factor list will, of course, be the gaze direction. Right. So we are going to display both the statistics and the plots. We are particularly interested in the plots because we want to see the extent to what we can consider that these data follow a normal distribution. And in plots, we are going to be interested in the histograms, not in stem and left, but in the histograms. And this is probably the most important box to check in this particular case, and it's normality plots with tests. So we are going to ask here to perform normality plots in SPSS. So it's going to perform Shapiro-Wilks, and that's the test that we want to run in order to see whether it is a normal distribution or not. As we can see, we have different participants per condition. So 12 of them were looking at were assigned to the looking at the left condition, whereas 24 were assigned to the closed eye conditions. Basically, in this design, we had that all participants were rating or were deciding whether the suspect was being shown in the video when they were lined up with closed eyes. So there were 24 people rating them, and there was only 12 of the participants watching the lineups, looking at the left or at the center of the screen. Okay, it is important to be aware of these numbers, but basically we were planning to just test normality. So these are the descriptors, and this is the test of normality. So according to Shapiro-Wilk, all the conditions could be have been extracted from a normal distribution. So it's difficult with these data to think that they are not normal. That's what these probabilities are saying. So if we had to conclude that the distribution is not normal, we will be basically making a very high error. So the probabilities are too high, and therefore, because all of them are higher than 0.05, we can conclude that they follow a normal distribution. Right, let's have a look at the histograms. So this looks a little bit like a normal distribution. You can see that the data are there's few data, the data set is not too large, and therefore it's not easy to find clear patterns of normal distributions. So in these cases, that's why it's important to have a test of normality. When we have many data, then it's easier to look at the histograms, but in this case, we only had 24 participants and 12 of them for many of the cases. So, and then we have the QQ plots. Basically, it's the observed value plotted against the expected normal value. So, what would be expecting from a normal distribution, and we actually what we be observing. And as you can see, if they are very close to a line, to this line, then we can assume that they are normal. So normal QQ plots are clearer in this case than the histograms. We have 4, of course, one per condition. So left, right, center, closed eyes. Right, and then 1 week. And these are the box plots for the 1 week condition. So in this case, this is important because it's going to tell us whether we can accept another assumption. So we know that it's normally distributed because the Shapiro-Wilk test is telling us, and because the histograms look like a normal distribution, and the QQ plots are also telling us that it looks like a normal distribution. But we also want to know if we can assume that the variances of all the populations are homogeneous. So let's say that we have the population of people rating lineups looking at the left, and that would be this one. The population of people rating lineups looking at the center, and that would be this one. Looking at the right, or closed eyes. And this is the mean value. These black lines are the mean values, and the box is representing the variance. So in general, they are sufficiently close and they are sufficiently similar. So we would be saying that it's quite homogeneous. The data are more compact for the left condition than for the center condition. Center condition, it seems like they are more sparse, so it's not so compact in this case. Well, so let's have a look at the 6 months. We know that they are normal because we have that tests, and in this case the variance looks slightly more difficult. So we have more compact values here for left, and a slightly larger variance in here for center, but still they seem quite homogeneous. A good way to test homogeneity is not to just rely on this graphical version, but actually to just run an ANOVA. So if we just go to compare means, one-way ANOVA, then we can select the dependent lists here and the independent variable in factor, and then in options we ask for homogeneity of variance test. We could also include descriptives and so on, but basically this is what we are doing just now. So testing the homogeneity of variance for these for these two distributions. So let's see what we get. And then again, so this is the output that we are interested now in. So it is testing the homogeneity of variance, and as you can see, both of the significant values are way above 0.05, so we will be concluding that it is possible to run an ANOVA with these data, and the assumption of homogeneity of variance has been satisfied. So we have seen two different ways to test homogeneity of variance and normality.